Hello friends, in this video I am going to solve exercise question from book Topics in Algebra from chapter Vector Spaces and Modules. So question is, prove that the vector spaces in example 4.1.4 and example 4.1.2 are isomorphic. Note that example 4.1.4 in the book is Vn is a subset of vector space of all polynomials in X, and Vn consists of all those polynomials in X whose degree is less than n. So Vn is the vector space over field F consisting of all polynomials of degree less than n. And example 4.1.2 is V is the vector space over field F of all ordered n tuples alpha 1, alpha 2 up to so on alpha n, where each alpha I comes from field F, that is each alpha I is a scalar, and V is vector space consisting of all ordered n tuples of this kind. Now here we want to show that vector space V and vector space Vn are isomorphic. Firstly, we will recall definition of a homomorphism in vector spaces. So if U and V are vector spaces over field F, then the mapping T from U to V is said to be a homomorphism if T of U1 plus U2 is equal to T of U1 plus T of U2, and T of alpha U1 is equal to alpha times T of U1 for all U1 U2 in U and for all alpha in F. So this is the concept of homomorphism in vector spaces. Next concept is concept of kernel of a homomorphism. We will need this in our proof. So kernel of a homomorphism T from vector space U to vector space V is defined as kernel T is set of all those vectors U in U such that T of U is 0. That means kernel T is collection of all those vectors U in vector space U which under T get mapped to 0 vector in vector space V. Now we are ready to prove this result that V and Vn are isomorphic. So for this, firstly we will define a map, say phi from vector space V to vector space Vn as phi of alpha 1, alpha 2, alpha n, that is under phi these ordered n tuple get mapped to this polynomial alpha n x to the power n minus 1 plus alpha n minus 1 x to the power n minus 2 plus and so on plus alpha 1. Now claim is to show that phi is an isomorphism. To show phi is an isomorphism, firstly we will need to show that phi is a homomorphism. Now to show phi is a homomorphism, consider any two ordered n tuple, say a1 a2 an and b1 b2 bn in V. Then phi of a1 a2 up to so on an plus b1 b2 up to so on bn will be equal to phi of, we need to add this two ordered n tuple first, so that will be a1 plus b1 comma a2 plus b2 up to so on an plus bn. Now under phi this ordered n tuple will get mapped to this polynomial which is a1 an bn x to the power n minus 1 plus an minus 1 bn minus 1 x to the power n minus 2 plus and so on plus a1 plus b1. Now note that this polynomial is addition of these two separate polynomials which are an x to the power n minus 1 plus an minus 1 x to the power n minus 2 plus and so on plus a1 plus bn x to the power n minus 1 plus bn minus 1 x to the power n minus 2 plus and so on plus b1. Now this polynomial is image of the ordered n tuple a1 a2 up to so on an under phi, and this polynomial is image of the ordered n tuple b1 b2 up to so on bn under phi. So finally we get phi of a1 a2 up to so on an plus b1 b2 up to so on bn is equal to phi of a1 a2 up to so on an plus phi of b1 b2 up to so on bn. Next thing is to show that if lambda is any scalar in field F and a1 a2 up to so on an is any ordered n tuple in vector space V, then phi of lambda times a1 a2 up to so on an is equal to lambda times phi of this ordered n tuple. So we will do that. Now we have phi of lambda times a1, a2 up to so on an will be phi of this ordered n tuple lambda a1, lambda a2 up to so on lambda an. Now image of this ordered n tuple under phi will be this polynomial, that is lambda an x to the power n minus 1 plus lambda an minus 1 x to the power n minus 2 plus and so on plus lambda a2x plus lambda a1. Now for this polynomial we can take lambda common since each term is multiplied with lambda. So taking lambda common we get this thing. Now this polynomial is image of the ordered n tuple a1, a2 up to so on an under phi. So we get finally phi of lambda times a1, a2 up to so on an is equal to lambda times phi of a1, a2 up to so on an. So this shows that from here and from this that phi is a vector space homomorphism, or we can just say phi is a homomorphism. Now next thing is to show that phi is 1 1, because we need to show that phi is a isomorphism, and to show phi is a isomorphism we have just shown phi is a homomorphism, so only need thing remains to show that phi is 1 1. For this we will use the theorem which states that a homomorphism T from vector space U to vector space V is an isomorphism if and only if kernel T is singleton 0. So here to show phi is 1 1 we will show that kernel of phi is 0, which will prove our claim that phi is isomorphism. So to show kernel phi is singleton 0 we will assume any arbitrary ordered n tuple, say a1, a2, an in kernel phi. Now as this ordered n tuple is in kernel phi, we have phi of a1, a2 up to so on an will be equal to 0 x to the power n minus 1 plus 0 x to the power n minus 2 plus and so on plus 0x plus 0. This is the 0 polynomial in V. In Vn. Now phi of this ordered n tuple will be this polynomial, and which is equal to the 0 polynomial. Now as these two polynomials are same we can compare their coefficient. So we get, after comparing coefficients, an is equal to 0, an minus 1 is equal to 0 up to so on, a2 is 0 and a1 is 0. So in this ordered n tuple, or this ordered n tuple will be equal to this ordered n tuple 0 0 up to so on 0. Now this is any arbitrary element in kernel phi, so we get kernel phi is this. Kernel phi is the set consisting of just ordered n tuple, this or we can say 0 vector in vector space V. So as kernel phi is singleton 0 vector, kernel phi or phi will be 1 1 map, and therefore from 1 and 2 we have map phi from vector space V to vector space Vn is an isomorphism, and this shows that vector space V and vector space Vn are isomorphic, and this proves our claim.